Hello, this is my Lab 3 Magnetic Fields of Bar Magnets video. This presentation will be split into 7 sections: an introduction, a procedure, qualitative observations, quantitative observations, calculations and results, a model, and finally a conclusion. So in this experiment, we were asked to use the magnetometer application as well as a bar magnet to experimentally confirm theoretical formulas. We also determined the magnetic dipole moment of the bar magnet using a linear regression technique. And finally, we modeled the magnetic field of the bar magnet for observation locations on axis, on a perpendicular axis, and on a 45-degree axis. The fundamental physical principles involved were the magnetic fields, bar magnets with north and south poles, and magnetic dipoles. And this is the formula of a far field approximation of the magnetic field due to a dipole. And at the end of the experiment, we found the value of n, which is a theoretical value, and the value of mu, which is the magnetic dipole moment of the bar magnet. These values are shown in the table. So now for the procedure. So I used the Physics Toolbox iOS application to measure magnetic fields and their components. Uh, First, I calibrated the magnetometer application. Uh, Next, I used the bar magnet along with the meter stick to locate the magnetometer on my iPhone using various minimization and maximization techniques. Uh, Next, I measure the distance from the on-axis bar magnet to the magnetometer for various magnitudes of the x component of the magnetic field. And finally, I measure the strength of the components of the off-axis magnetic field on a 45-degree axis using the magnetometer application. So now for observed constants and qualitative observations. So I found that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. I also find that as the magnetometer moves closer to the magnet, the measured magnitude of the x component of the magnetic field increases. The geographic net magnetic field I found at the location where I'm doing the experiment was 5.188 times 10 to the negative 5 teslas. Now for quantitative observations. So the first table shows the average distance r from the magnetometer that resulted in a given magnitude of the x component of the magnetic field. Uh, and the second table shows various measured quantities that helped me find the net magnetic field uh, in the 45-degree axis. And now for calculations and results. So the chart on the left shows the data calculated from step 1 of the experiment, as well as the line of best fit. And we can use this line of best fit and actually map it to the equation shown here, n times ln of r plus ln of k. And we can see that n is simply the slope of this line, which is negative 2.645. And we see that the theoretical value of n, negative 3, is very close to this experimental value of n. We also see that the y-intercept of this line is simply ln of k. And we can use this value ln of k to solve for k, and then to subsequently solve for the magnetic dipole moment mu, which we find to be 2.545 amps times meters squared. Next, we have our model. So here we have the dipole B function, which calculates the magnetic field due to a dipole using the far field approximation shown in the introduction. And also I have code for for calculating and displaying the off-axis magnetic field. For sake of brevity, I don't show the on-axis and perpendicular axis magnetic fields because they're very similar to this. And in the diagram itself, we can see the orange arrows represent the on-axis magnetic field. The cyan arrows represent the magnetic field in the perpendicular axis, and the magenta arrow representing the off-axis or 45-degree axis magnetic field. And notice that the direction of the arrows, and notice the direction of the arrows, which are different from the on-axis and the perpendicular axis. From this table, we can see that the magnitude of the experimental value of the magnetic field off-axis is larger than the computationally calculated value. We can also see that the experimental value has a z component, whereas the computational value does not, indicating some experimental error. If we had not calibrated the to magnetic north, we would see that the line of best fit shifts right, which would increase the y-intercept, which would increase k, and which would subsequently increase mu. However, n would stay constant as the slope stays constant. Also, if two magnets were stuck end to end, the magnitude of the magnetic field will increase due to the law of superposition. However, the direction of the magnetic field at the observation location will not change. Thank you.